Hello YouTube. In this series we're going to take a look at scientific experiment. Experiment is of course absolutely crucial in science. It's what really distinguishes scientific inquiry from other domains. I think it's worth taking a look at how scientific experiments actually work. Now, I should say this series is probably going to be a little less philosophical than usual, just because I'm going to look more at how experiments are actually done in practice and the kind of practical problems that scientists face, but we will still be drawing on philosophy where it's relevant, and I think this is going to be a good supplement to the Philosophy of Science series. So I'm mainly drawing on the book Experimental Design for the Life Sciences by Ruxton and Colgrave, which is a really fantastic book. It's very clear, very straightforward, so I strongly recommend that if you want more details. Obviously this is based a bit more in biology, and I know more about biology, which is why I'm taking that angle on it. Experiments in physics, for instance, may well be quite different, so that's something that's worth keeping in mind as you're watching this series. Okay, so the first thing to point out is that before doing an experiment, we need to have some idea of what it is we want to test. In particular, we need to figure out a specific research question and then develop a specific hypothesis where we can gather data that will either support or falsify the hypothesis. We need a hypothesis that can be used to make predictions about what we will observe under certain specified conditions, and then we go and gather those data. So I think it's worth starting with a particular example. Now, an important figure in public health is Ignaz Semmelweis, who lived in the 1800s, and at the time one of the most serious causes of death among women was childbed fever, which occurred following childbirth. Childbed fever is caused by bacterial infection, but when Semmelweis was working, that wasn't known because they didn't have the germ theory of disease. Now, Semmelweis worked in a hospital in Vienna, which had two maternity clinics. The first clinic had a mortality rate of about 10% due to childbed fever. The second, only about 4%. And Semmelweis wanted to know, well, why was this? Right? Why are the rates of childbed fever higher in the first clinic than in the second clinic? So notice that we have here a very specific question, right? We're not just asking, well, how can we stop childbed fever? I mean, we do want to stop childbed fever, but in science we need to be a bit more specific, right? Be more precise if we're going to perform experiments. The point about this question is we can use this question to generate testable hypotheses. And Semmelweis generated a variety of hypotheses to answer this question. One hypothesis that he came up with was, well, maybe the higher mortality rate in the first clinic is due to overcrowding. And obviously the prediction that one can make from this hypothesis, an obvious prediction, is that the first clinic will tend to be more crowded. That was fairly easy to test. Semmelweis just checked the rates of crowding in the two clinics, and in fact, the second clinic tended to be more crowded than the first. So this hypothesis was disconfirmed because there was actually less crowding in the first clinic. An interesting hypothesis that was considered by Semmelweis was so the first clinic was set up so that whenever a priest went to see a dying woman in the sick room, he would pass through the clinic in view of the pregnant women. On the other hand, in the second clinic, the priest was able to access the sick room directly, so the women there didn't see him. So Semmelweis wondered if seeing the priest, who of course was associated with times of death and so on, he wondered if seeing the priest led to fear and stress in the women, and maybe this stress caused them to weaken or whatever and make them more susceptible to childbed fever. So he had this hypothesis that the high rate of childbed fever in the first clinic is due to visits from the priest causing stress among pregnant women, and he derived the prediction that if the priest is removed from the sight of the pregnant women, the rate of childbed fever will decline. So Semmelweis instructed the priest to take a different route when visiting the first clinic, and obviously it made absolutely no difference. And Semmelweis worked through a whole bunch of different hypotheses. Was getting a little bit desperate, but eventually had a breakthrough. You see, in the first clinic, women were tended to by medical students who also performed various other operations, including autopsies. So these medical students would visit the pregnant women after doing autopsies, and they'd maybe superficially, wash their hands, but, just sort of in plain water, just to wash the visible bits off. But it was only sort of superficial. The second clinic, on the other hand, was staffed by midwives who focused only on the pregnancies. So Semmelweis thought that there might be some kind of contamination from the what he called cadaveric matter from the dead bodies in the first clinic. So the high mortality rate of the first clinic is due to contamination by cadaveric matter from corpses. Now, as I said, the germ theory of disease was unknown at the time. So the idea was that it was decaying matter from a dead body, which, when introduced into the bloodstream, caused the fever. So we get the prediction that if the medical students remove all cadaveric matter before examining the women, mortality rate will decline. Now, there's quite a serious problem with this particular prediction, because presumably some of the cadaveric matter will be too small to see. So how do you know when you have removed it? I mean, this is a prediction which, as stated, is untestable, because, at least in Semmelweis's time, he had no way of knowing whether or not all of the cadaveric matter had been removed. So we need to then maybe make some guesses or assumptions. And Semmelweis found that thoroughly washing the hands in a solution of chlorinated lime was the best way to remove the smell following the autopsy. So obviously, do an autopsy, you're not just going to have bits of matter on your hand, there's going to be the smell. And Semmelweis found that this solution of chlorinated lime was the best way of getting rid of the smell. And I guess it's a reasonable assumption that if you can't smell it anymore, then the cadaverous material has been destroyed or removed. So with that assumption, we get the prediction that if the medical students thoroughly wash their hands in a solution of chlorinated lime before examining the pregnant women, the rate of childbed fever will decline. And when Semmelweis instructed the students to do this, straight away the mortality rate plummeted to match the rates in the second clinic. So we have a confirmed prediction. Now, just as a bit of an aside, this is actually quite a sad story, because Semmelweis's views were rejected at the time. And it was many, many years before hand washing was made a requirement. Semmelweis became increasingly angry with the medical establishment. He basically had a nervous breakdown, and because he was sending all of these angry letters off to various doctors and various people in the medical establishment, accusing them of basically murdering women because they refused to institute these policies of hand washing. And in the end, he was committed to a mental institution where he died after being beaten by the guards. So quite a sad story. But it's quite a nice example of how scientists go about, generating testable hypotheses and generating predictions and testing them. Now, there are 2 points that I think are worth bearing in mind about this Semmelweis case. 2 points that this illustrates. First of all, doing science isn't simply a matter of gathering data, right? You don't just make a whole load of observations and then build your theory or hypothesis on them. So you don't just sort of sit down and observe pregnant women for several hours a day, just gathering as much data as you can. Data on its own is almost totally useless. You need to have some idea of what it is you're looking for. You gather data for the purposes of testing a particular hypothesis. And so, of course, you can see that with the different hypotheses that Semmelweis proposed, you get very different kinds of data that you then have to kind of gather to test them. So that's just a practical point about how experiments work. A second point is it's important to bear in mind that Semmelweis's hypothesis was actually false. Today we know that it's not the cadaveric matter that causes the infection. It's rather the bacteria that grows on the cadaver. This is quite a general point here. Whenever a prediction derived from a hypothesis is confirmed by experiment, we're not showing that the hypothesis is true. What we've done is derive a prediction from the hypothesis, and the prediction has shown to be true. But the key point is that there are always other hypotheses that will lead to the same prediction. So any time a hypothesis is confirmed, right, there are always many other hypotheses that will equally be confirmed. Maybe it would be a useful little task at this point to pause the video here and try to come up with your own hypothesis that would have led to the same prediction as Semmelweis's. But if you don't want to do that, no problem. Here's an idea that I thought of. So remember, here's Semmelweis's prediction that if the medical students thoroughly wash their hands in chlorinated lime before examining the pregnant women, childbed fever will decline. So here's my alternative hypothesis that would lead to this. So the medical students were male and the midwives were female. Perhaps there's some sort of chemical difference between the male and the female hands. So maybe male and female hands, males and females produce different kinds of sweat, say. I mean, after all, we know that men and women do have different levels of certain hormones in their bodies and so on. So maybe male sweat is different from female sweat, and male sweat is poisonous to women when introduced into their bloodstream. Which obviously, if you're doing medical examinations, you may end up getting into the bloodstream. However, thoroughly washing in chlorinated lime will tend to clean off the sweat. So it will be fine for the medical students to examine the women. So we have two hypotheses here which lead to the same prediction, that if medical students wash their hands in chlorinated lime, childbed fever rates will decrease. So now, of course, we're going to have to come up with some more predictions to distinguish these hypotheses. Maybe an obvious test would be to have the midwives do the same thing as the medical students, right, and handle some corpses before examining the women. And then the prediction in that case is, well, I mean, look, if the cadaveric material is not dangerous, then it won't make any difference if the midwives handle the cadavers. So let's say we were to perform this test and the mortality rates in the second clinic remained low. Well, that would suggest that indeed it has not actually got anything to do with the cadaveric material, right? So Semmelweis's cadaveric hypothesis is false. Anyway, the key point here is just that having a confirmed prediction doesn't show that your hypothesis is true. You can come up with other hypotheses almost indefinitely that will be compatible with the outcome of your test. In the philosophy of science, this is known as the problem of underdetermination. The evidence that we have underdetermines which hypothesis or theory we should accept. Many hypotheses are compatible with the evidence. I have a whole video on underdetermination, which is part of my series on scientific realism, which you can check out if you want. But a useful way to think about this is to imagine a graph. So let's say we're collecting some data and we plot it on a graph. It doesn't really matter what the data is, but say we have something like this. Now let's suppose that these are points on some underlying line. Now the point of underdetermination is there's an infinite number of lines that can be drawn through these points. The obvious one, of course, would just be a straight line, but we could draw almost anything, right? As long as the line we draw goes through these points, we can draw anything. And no matter how many points you add to the graph, there will always be many lines that you could draw through them. So here the shape of the line is underdetermined by the points. And of course the analogy here is that the points represent the data, the observations, and the lines that we could put through them represent the hypotheses. So it's a very fundamental feature of the logic of science that we can never prove any hypothesis conclusively. There's always the possibility that new evidence will show that our hypothesis is wrong. Right. So that's Semmelweis and a few points that are made, I think, by the Semmelweis case. I think now it's worth just laying down a bit of terminology at this point. So scientists draw a distinction between the dependent variable and the independent variable. Let's say that we want to know how some feature A is affected by some other feature B. Well, in this case, the dependent variable is A, so this is what is being tested. The independent variable is B. When we conduct an experiment, the independent variable is what we change or control to test the effects on the dependent variable. So we change or control B to see its effects on A. So that the dependent variable is dependent on the independent variable. So in the Semmelweis case, when Semmelweis instructed the doctors to wash their hands in chlorinated lime, the dependent variable was the mortality rate in the first clinic, and the independent variable was the rate of hand washing before examining the women. Semmelweis wanted to see how hand washing would affect mortality rates. And as we saw, the mortality rate was indeed dependent on hand washing. So that's just an important distinction that that kind of we need to make here. Right. Broadly speaking, there are two types of experiment: manipulative and correlational. So in a manipulative experiment, the experimenter alters the system and measures the effect of the changes. So we can think of this as variation in the system is created artificially. On the other hand, in a correlational experiment, the experimenter observes the system without altering it. So the naturally occurring variation in the system is used. So to sort of see the differences between these experiments, let's say we are studying turtles, and we find that some turtle shells have certain types of humps on them. And we want to know, why did the turtles develop these humps? So one thought might be that it has something to do with their swimming. Maybe the humps provide stability or catch the currents in a certain way or whatever. And this gives us the hypothesis that humps on turtle shells evolved to improve swimming ability. And I guess we would then derive the prediction that the turtles with larger humps will swim more efficiently. Okay, so two ways of studying this. We have the sort of manipulative method and the correlational method. Now, in a manipulative experiment, we would have to, say, do something like alter the size of the turtle shells. We might divide the turtles into three groups. In the first group, you simply cut off the humps. In the second group, you cut off the humps and then stick them back on again after increasing their size somehow. You cut them off, increase the size, and then reattach them. And in the third group, you cut off the humps and then stick them back on again without changing their size. And the third group here is the control group. Now, obviously, the reason why you have to cut off the humps in all of these cases is that you need all the three groups of turtles to undergo the same experimental manipulation, because otherwise any differences you detect between the groups could just be due to one of the groups having undergone the operation, right? So if we cut off the humps in group 1, but then we didn't perform any removal of the humps in groups 2 and 3, then if we did find a difference between group 1 and the other groups, it could just be because of the operation itself, rather than because of the sizes of the humps. So you want to make sure that all the groups are the same, with the exception of the independent variable of hump size. Anyway, after doing this, you then, say, observe how the turtles swim. And if the hypothesis is that humps evolved to improve swimming ability, then I guess we would expect those without the humps, those in group 1, to swim worse, and those in group 2 to swim best. On the other hand, a correlational experiment would involve simply finding a study site and observing the turtles swimming. If we see that turtles with larger humps tend to swim in a different, perhaps more efficient way, that would support our hypothesis. We're not manipulating anything, we're just using the natural variation in humps to test the relationship between hump size and swimming. So those are two approaches that scientists can take when testing hypotheses. Now, each type of study has some problems. So let's think about some problems with manipulative experiments. Well, the first point is that manipulation can have unintended consequences. Manipulating one part of any system will have various effects on the system which are very hard to control. So the very act of handling a turtle so as to alter its humps may change the turtle's behaviour in ways that have nothing to do with hump size. Manipulating animals will often cause them stress, say. And so in general, in most systems, there's going to be a very complex causal web of interactions, and any disturbance can ramify through the system. I mean, this is especially true really for organisms, because organisms are very complex, very well integrated systems. You know, they've got lots of different parts that are all sort of functioning together as an integrated whole. And if you consider cutting off part of a shell and then reattaching it, well, you know, an organism isn't a machine where you can just remove parts and then put them back on. So that very act of manipulation is going to have various consequences on how the turtles behave. And so that's one quite serious problem with any manipulative study. A second problem is that manipulation that we do may not be biologically relevant. We might modify a turtle so that its humps are far larger or far smaller than would be normal, but then it's not really clear that we can extrapolate from any results to conclude anything about turtles in the wild, you know, as they actually live in nature. Because if we've manipulated turtles so that their humps are far larger than normal, then we've been studying something that's outside the naturally occurring norm. I mean, this would obviously be a problem if, say, we were to make the humps 10 times bigger than normal. Even if we think that larger humps improve swimming ability, there's obviously going to be a limit to that. Humps that are too large will interfere with swimming. Another, I guess, extreme kind of manipulation, which is done all the time, is when animals are studied in a laboratory. The laboratory is often an environment which is far outside the sort of normal, natural range, the normal kind of environment in which those animals live. And so that's just living in a laboratory is going to have significant consequences on their behaviour. So we've got to keep in mind that any manipulation, even if we do try to keep it within the natural range, but any manipulation is going to be a product of our interference, and in that sense is unnatural. And so in that sense there's going to be a question about whether it's actually biologically relevant and whether we can really extrapolate from any study. Okay, third, well, sometimes manipulation is just impossible. Think about studies, say, of macroevolution. So this is how macroevolution is evolutionary processes at work over millions of years. We just can't manipulate that. And sometimes there are going to be ethical constraints. This is especially true in the medical sciences. We can't investigate the effects of lead on children by exposing children to lead. So, you know, that's just a general problem that we're going to face with a lot of manipulative studies. So why do people bother with manipulative studies at all, given all of these problems? Well, correlational studies have two serious drawbacks. First of all, they tend to be very vulnerable to confounding factors. Let's say that we find a correlation between two factors A and B. Well, as I'm sure you know, correlation is not causation. Perhaps A and B are correlated because they're both influenced by some third factor, C. In this case, C is the confounding factor. So, in other words then, a confounding factor is a variable that influences both the dependent variable and the independent variable. For example, in our correlational study of the turtles, let's say that we find that indeed turtles with larger humps do tend to swim better. And so, yes, this does confirm the hypothesis that the humps evolved to improve swimming ability. But there are many things that might be going on here. So maybe our hypothesis is right, and the humps evolved to improve swimming ability. Another possibility is, well, maybe all turtles have a tendency to grow these humps, but only when they're in good health, when they have a good diet and a strong immune system and so on. So good health causes the larger humps. Now, it's also likely that turtles in good health will be able to swim better than those in poor health. Good health improves swimming ability. So on this hypothesis, the correlation between the humps and the swimming ability is because both are caused by good health. There isn't any causal connection between the humps and the swimming. So just to take another example, suppose we're testing the hypothesis that LSD use causes mental illness. And we do a study which shows that, yes, there is indeed a correlation between the use of LSD and mental illness, right? People who use LSD have higher rates of mental illness than the general population. Well, an obvious confounding factor here is it might be that people with certain personality types tend to be more attracted to drug use, and those personality types also have a greater predisposition towards mental illness. So we might expect that the kind of people who are going to be attracted to LSD in the first place, they're going to be outsiders, maybe sort of counterculture, unusual, more creative, that type of person. And it could be that type of person is just more natural, just anyway disposed to mental illness, more so than other people. So the LSD use and the mental illness are both influenced by underlying personality traits. Now, that's just an example. I don't know if that's, I don't know the research there, but you can sort of see how that works. And manipulation allows us to address this problem. So to return to the turtle humps then, if we alter the turtle humps to make some smaller and some larger, then we know that hump size isn't going to be tied to overall health. However, it's worth bearing in mind that although manipulation does allow us to control for the confounding factors that we think of, manipulative studies are also vulnerable to confounding factors, right? So in the manipulative experiment on the turtles, where we have those three groups, we performed the same experimental manipulation on all three groups, even those whose humps were not being shortened. But suppose we hadn't done this. Suppose we only cut off the humps of turtles in group 1. Well, that would have introduced a confounding factor. Because if we then found that turtles in group 1 do indeed swim badly, well, is that because the larger humps are important for swimming, or is it because of the stress or whatever caused by having the humps cut off? So, in any manipulative study, we have to be careful not to introduce confounding factors in the course of our manipulation. Manipulative studies don't eliminate the problem of confounding factors, but they're less vulnerable to it than a correlational study is. Okay, the second problem for correlational studies is reverse causation. So having established a correlation between A and B, reverse causation is the mistake of thinking that A causes B when in fact B causes A. Consider the hypothesis that lack of physical exercise increases the probability of developing depression. So we conduct a correlational study and we find that indeed people with depression have lower rates of physical activity. Now, of course, this does confirm our hypothesis, right? This confirms the hypothesis that physical inactivity causes depression. However, we have to bear in mind this could be a case of reverse causation. We do know, after all, that people who are depressed don't like going out, they don't like doing a lot of movement, so perhaps it's just that depression leads to physical inactivity. But being more active in itself has no effect on depression. And again, if we were to manipulate the independent variable, so let's say we instruct people with depression to start exercising more, well, in that case, if the rates of depression decrease, that would lend better support to our hypothesis that physical inactivity causes depression. Okay, if we actually make people go out and do exercise, and then we test what effect that has, then we could rule out the idea that it's just that the correlation is just because depression is causing physical inactivity. Okay, so that was just a kind of basic introduction to how scientific experiment works and some of the different types of scientific experiment, and we'll have more to say about this in later videos. But that's all for now. Thank you for watching. Goodbye.